This video is about speed time and velocity time graphs. As the title suggests, we will discuss speed time and velocity time graphs. We will begin with speed time graphs. Let's draw a speed time graph for the motion of a boat. We will use this grid. The boat starts from rest, so initially its speed is 0. Then in 20 seconds it reaches a speed of 10 meters per second. So for the first 20 seconds, the graph looks like this. Constant speed means that there is no change in speed. So for the next 30 seconds, the graph is horizontal. Finally, the boat takes 10 seconds to slow down and stop. So in the next 10 seconds, its speed drops back to 0. There are two key points to remember about speed time graphs. The first is about the gradient of the graph. Since on the vertical axis we have speed and on the horizontal axis we have time, the gradient is change in speed over change in time. Change in speed over change in time is acceleration, so the gradient of a speed time graph represents acceleration. Let's find the acceleration of the boat when it's speeding up and when it's slowing down. This is the section where the boat is speeding up. The change in speed is 10 meters per second and the change in time is 20 seconds. This means that the acceleration when the boat is speeding up is 10 meters per second over 20 seconds, and this is equal to 0.5 meters per second squared. When the boat is slowing down, the change in speed is also 10 meters per second, while the change in time here is 10 seconds. So the acceleration when the boat is slowing down is 10 over 10, so 1 meters per second squared. Remember that acceleration is a vector, so this 1 meters per second squared is the magnitude of the acceleration. Here the boat is slowing down, in other words, decelerating. When an object is decelerating, we usually say that its acceleration is negative. We will talk a bit more about the sign of the acceleration when we get to velocity time graphs. Next, let's see what the area under the graph means here. I will not go into the mathematical details of why, but will just state here that the area under the graph represents the distance traveled by the boat. A quick way to confirm this is to multiply the units on the vertical and the horizontal axes. Doing this, we get meters per second multiplied by second, so second is cancelled and we are left with meters, which is a unit of distance. As a side note that might be useful, if you're not sure in a question what the area under the graph represents, just do what we've done here and multiply the units on the two axes. The resulting unit that you get is the unit of the quantity that is represented by the area under the graph. Let's figure out the total distance traveled by the boat. To do this, we will split the area into two triangles and a rectangle. Remember that the area of a triangle is base times height divided by 2, and the area of a rectangle is length times width. So for the total area, we get the area of the rectangle on the left, which is 20 times 10 over 2, plus the area of the rectangle, which is 30 times 10, plus the area of the triangle on the right, which is 10 times 10 over 2. So for the total distance traveled, we get 450 meters. Let's move on to velocity time graphs. This graph shows how the velocity of a car varies with time. On this graph, just like on displacement time graphs, the vertical axis has positive and negative values. This is because velocity is a vector, so it has a direction. For this graph, let's assume that when the car is moving to the right, it's moving in the positive direction, and when it's moving to the left, it's moving in the negative direction. These choices, just as on displacement time graphs, are arbitrary. Let's see what we can read from this graph. During the first 10 seconds, the car moves to the right, and its speed increases from 0 to 20 meters per second. Here, the car travels at a constant speed of 20 meters per second for 20 seconds, then it brakes and comes to rest in 5 seconds. Notice that during all this time the car is moving to the right, first speeding up, then moving at constant speed, then slowing down and coming to rest. For the next 15 seconds, the car's velocity is 0, so it is standing in one place. Then here it starts moving again, and since the velocity is negative, the car is now moving to the left, and it takes 10 seconds to speed up from rest and reach 10 meters per second. Here the car is still moving to the left, but now at constant speed, and after traveling 20 seconds at a constant speed of 10 meters per second, it takes another 20 seconds to slow down and stop. Let's discuss some key concepts related to this graph. Just like on speed-time graphs, the gradient of the graph represents acceleration. When a, the acceleration, and v, the velocity, have the same sign or direction, the car is speeding up, and when they have opposite signs, the car is slowing down. Another important, although a bit more obvious point, is that the sign of the velocity shows the direction in which the car is traveling. Since on this graph we chose right to be the positive and left to be the negative direction, when the velocity is positive, the car is moving to the right, and when it's negative, the car is moving to the left. Let's see a question related to this graph. We will describe the motion of the car in detail between t equals to 50 and 60 seconds. When we started, we briefly discussed what type of motion each segment represents. Here we will just go into a bit more detail for our chosen segment. So let's see what happens between 50 and 60 seconds. Since the velocity here is negative, the car is moving to the left. Looking at the graph, we can see that the gradient is negative. This means that the acceleration is also negative. Since v and a have the same sign, both of them are negative, the car is speeding up. This also makes sense when we look at the graph, because in this section the graph is moving further away from the horizontal axis. Generalizing this idea, we can say that when the graph is moving away from the horizontal axis, speed is increasing, and when it's moving towards the horizontal axis, speed is decreasing. When the graph is horizontal, the car is traveling at constant speed, or if the graph is on the horizontal axis, the car is at rest. Finally, let's calculate the magnitude of the acceleration, which is the magnitude of the gradient. Since the velocity changes from 0 to -10, the change in speed is 10 meters per second, and this is divided by change in time, which is 10 seconds. This gives us 1 meters per second squared for the magnitude of the acceleration. Next, let's see what the area under the graph represents here. So the area under a velocity time graph represents displacement. Remember that displacement is a vector, and its magnitude shows how far the object is from its starting point. The displacement also has direction, and this tells us whether the car is located towards the positive or the negative direction from its starting point. Because of this, when we are calculating the displacement, areas above the horizontal axis are taken to be positive, and areas below the horizontal axis are taken to be negative. The area under the graph can also be used to calculate distance traveled. However, here all areas are taken to be positive. Let's find the displacement and the total distance traveled by this car. Earlier in this video, when finding the area under the speed time graph, I worked with the area of two triangles and the rectangle. Here, I will take a slightly different approach and use the area formula for a trapezium. Based on this formula, I will add the two bases of the trapezium, multiply this sum by the height, and divide by 2. So for the area of the first trapezium, we get the lower base, which is 35, plus the upper base, which is 20, multiplied by the height, which is also 20. This is then divided by 2, which gives us 550. The area of the second trapezium is the upper base, so the one on the time axis, which is 50, plus the lower base, so 20, multiplied by the height, which here is 10. This is divided by 2 and gives us 350. Let's calculate the displacement. The first area is above the horizontal axis, so it's taken to be positive, while the second area is under the horizontal axis, so it's taken to be negative. This gives us 200 meters. We get a positive number here, which means that the displacement is in the positive direction. Since we have taken the positive direction to be towards the right, the displacement of the car at the end of its motion is 200 meters to the right of its starting position. Finally, let's find the distance traveled. Since here all areas are taken to be positive, we get 550 plus 350, and this is 900 meters. Let's summarize what we have learned in this video. We have seen that on speed-time graphs, the gradient represents acceleration, added that a positive gradient means that the object is speeding up, and a negative gradient means that the object is slowing down, and we discussed that the area under the graph represents distance traveled. On velocity time graphs, similarly, the gradient represents acceleration, but here, when the sign or the direction of the velocity and the acceleration are the same, the object is speeding up, and when they have different signs, the object is slowing down. We learned that here the area under the graph represents displacement, and when calculating displacement, the areas above the time or horizontal axis are taken to be positive, and those below are taken to be negative. Finally, we mentioned that when calculating the distance traveled, all areas must be taken to be positive. This wraps up our discussion about speed time and velocity time graphs. In the next video, we will discuss equations of motion for uniform acceleration, more commonly known as Suvat equations.